Hello and welcome to Cashmatics. Now I've got a treat for you today, and what a treat it is. We're going to be talking about the factor theorem and polynomial division. So try to contain your excitement, grab yourself some paper and a pen, and let's get started. The first thing we need to do is define what the factor theorem is, and what it says is if x equals a is the root or solution of the equation f of x equals 0, then x minus a is a factor of f of x. Now that's quite a mouthful, so the best way to explain it would be via an example. So let's say we've got f of x is x squared plus 2x minus 15, and what I'm going to do is I'm going to just stick a few numbers into f of x and see what result I get. So the first one is when x equals 1, and I'm just going to put 1 into this equation. So 1 squared plus 2 times 1 take away 15, and that gives me 1 plus 2 take away 15, which is minus 12. If I was to plug 2 into that equation, I'd get 2 squared plus 2 times 2 take away 15, which is 4 add 4 take away 15, which is minus 7. If I was to put 3 into that equation, I'd get 3 squared plus 2 times 3 take away 15, which is 9 plus 6 take away 15, which is 0. Okay, so compare that to what the factor theorem states. Okay, and if I was to put minus 5 in there, I get minus 5 squared plus 2 times minus 5 take away 15, which is 25, take away 10, take away 15, which is also 0. So these two results here do have something to do with our factor theorem. We can see that f of x, or f of 3, f of minus 5 is 0, which means that x minus 3 and x plus 5 is a factor, because this says that x take away minus 5, which is the same as x plus 5, okay, and this would be x minus 3 according to the factor theorem. But where does all of that come from? Now let's just have a look at the factorized version of this f of x. If I was to factorize this, I would get x minus 3 x plus 5. And it makes sense now. When you see it like this, it does actually make sense, because if I was to put 3 into this, so that would be 3 take away 3, which is 0. So 0 times whatever would just be 0. Okay, or if I was to put minus 5 into this here, I'd get minus 5 plus 5, which is 0, multiplied by anything would be 0. So hopefully you can see where that factor theorem comes from. And what we're going to do is we're going to use the factor theorem to help us to solve equations which are not so easy to solve without this. So things like cubics and quartics. And what we'll do first of all is we'll practice some polynomial division, which is going to help us as well. And then we put all the things together and hopefully solve some quite complicated equations. Now before we do any division with algebra, we're going to do some division with numbers, and we're going to look at it in a little bit more detail and see what actually happens when we're dividing a number by another. And this process you really need to understand well in order to be able to apply it to the algebra. So let's just take a simple sum like this, 4,761 divided by 3. So we set it up like this, and I'm sure you've all seen that before. So we've got to ask ourselves a question. The first question is, how many 3's are there in 4? And the answer to that is 1. Okay, and normally what you do is you say, well, okay, well, 1 3 is 3. That's the remainder of 1, and you hook on a number 1 there to make that into 17. But we're going to do it slightly differently. Okay, rather than putting it there, we'll say 1 3 is 3, and 4 take away 3 is 1. Okay, so that's the remainder 1. That's where it comes from. But rather than hooking it over here, what we're going to do is we're going to bring the 7 down here instead, and we get exactly the same thing. So then we ask ourselves the same question, how many 3's are there in 17? And the answer is 5. And then we do 5 times 3, which is 15, and look at the remainder, which is 2, and rather than hooking it on over here, what we'll do is we'll bring the 6 down here. We ask ourselves, how many 3's are there in 26? And the answer is 8. And 8 times 3 is 24. remainder 2, and then bring the 1 down here, and then ask ourselves how many 3's are there in 21, and the answer is 7. Okay, so that's where all those numbers come from, so where the remainders come from and how we apply them to the other numbers in the thing we're dividing. So let's go over to the algebraic version. Okay, so I've got x squared plus x minus 12 divided by x plus 4. Now those of you who can factorize quickly in your heads will realize that x plus 4 is one of the factors of x squared plus x minus 12, and the other one would be x minus 3. But let's just see where that would come from if we did it using polynomial division. Now it does work slightly differently to the numbers in the sense that we're only concentrating on this term to begin with. So we ask ourselves, how many x's are there in x squared? Or the other way you could think about it is, what do you multiply x by to make x squared? And the answer is x. Okay, x times x makes x squared. So you multiply the x by all of this now. Okay, x multiplied by x plus 4, which would be x squared plus 4x. And then we subtract. Now, when you're doing polynomial division, what you'll notice is that these two terms will normally be the same. In fact, they'll always be the same. Okay, and you're subtracting these. So x take away 4x would be minus 3x. So that's the remainder. And I need to hook it onto the next number. And if you remember in the numerical example, we were bringing the number down to the remainder instead. Okay, so that would be 3x minus 12. Let me just write that a little bit neater. Then I ask myself the same question. How many x's are in minus 3x? Or what do you multiply x by to make minus 3x? The answer is minus 3. Okay, and then I multiply minus 3 by this. So minus 3 times all of that gives me minus 3x minus 12, and when I subtract those we can see the remainder is 0. And we're expecting a remainder of 0 because we know x plus 4 is a factor. You know, we could see that from earlier. X plus 4 was a factor because if you were good enough at doing factorizing a quadratic in your head, you'd have seen that x plus 4 was a factor. So that's how I do it that's how I divide a quadratic by a linear term. And what we're going to do next is we're going to divide a cubic term by a linear term. So it has a few more terms, but the process is exactly the same. And hopefully you'll be able to follow along with me. And if you need to, or if you want to, you can pause the video and give it a go yourself. So let me just get the example up. Okay, so there's the example. And like I said, pause the video if you like. I'll give you a couple of seconds before I go on and see if you get the same result as me. Or if you didn't understand it before, just listen on and hopefully you'll get it this time. Right, so let's have a look then. So what we've got is 2x cubed plus x squared minus 7x minus 6 divided by x minus 2. So the first question we ask ourselves is, what do you multiply x by to make 2x cubed? And the answer to that is 2x squared. All right. Now you'll notice when I'm doing polynomial division, always write down terms with the same power of x above the original number that's being divided. It just helps me to see what's going on. But anyway, what we need to do now is multiply 2x squared by all of this. Okay, so 2x squared times x is 2x cubed, and 2x squared times minus 2 is minus 4x squared. So I need to subtract now, so this bit will cancel out, and this bit here, x squared take away minus 4x squared would give me 5x squared. So be careful with these negative terms. Then bring this down. Okay, that's like hooking your remainder on. And then ask yourself the question, what do you multiply x by to make 5x squared? And the answer is 5x. Okay, then multiply 5x by this. So that would be 5x squared take away 10x. Subtract to give you 3x. Bring this down. And then see, what do you multiply x by to make 3x? The answer is 3. And then multiply to get 3x minus 6. Okay, and when I subtract those, I get 0. So what that means is this cubic here divided by x minus 2 leaves me with 2x squared plus 5x plus 3. Okay, and you know, a cubic divided by a linear will give you a quadratic. Now what you could do from there is you could factorize this if you wanted to. Okay, you could factorize this. So let's see what we get there. You've got 2x and x. Now you can't always factorize them, but in this case we can. And let's see what we'd get. So I need a 1 here and a 2 here, and they'd both be positive, and that would give us 2x squared plus 2x plus 2x. Sorry, that should be a 3, sorry, not 2. Okay, so 2x squared plus 2x plus 3x plus 3. Okay, so that gives me the right quadratic. So what I've got here is I've got this cubic, which I've written as 3 linear factors. So that's one of the factors, and these are the other 2 factors. So I can say that the cubic can be written as x minus 2, 2x plus 3, and x plus 1. Okay. Now we've got it in a form now which makes it so much easier to solve. So if this was f of x, if that was f of x, and I wanted to solve f of x equals 0, now that I've got it factorized, I can just pull out the solutions. Okay, I've got x equals 2, I've got x equals minus 3 upon 2, and I've got x equals minus 1. So hopefully you can see how powerful a tool this polynomial division is. And what we're going to do next is we're going to actually try and solve a quartic instead. And we're going to be dividing a quartic by a quadratic. So a quartic divided by a quadratic should give us another quadratic. Or if you did a quartic divided by a linear, that'll give you a cubic. Okay, so the powers kind of work themselves out. But let's just do another example and see how that one works out. And here's my last example, and it really does look horrible. We've got a massive quartic here, and we've got a quadratic, and we're going to try and divide them. And they work in a similar way. When we're dividing, we consider the highest power of the thing we're dividing by when we're doing this. So I'll explain what that means as we work on. So first of all, what do you multiply x squared by to make x to the power 4? And the answer to that is x squared. Okay, now multiply x squared by all of this. Okay, so that will give me x to the power 4, take away 2x cubed, take away 3x squared. So I need to subtract these. These terms will disappear, and what I'll get here is 6x cubed, take away 4x squared, and bring this down minus 34x. Remember, all of this was our remainder, and we're going to hook it onto the other term. Right, so let's ask ourselves the question, how many x squareds go into 6x cubed, or what do you multiply x squared by to make 6x cubed? And the answer is 6x. And let's multiply 6x by this whole quadratic. So 6x cubed, take away 12x squared, take away 18x, and let's subtract again. Alright, so if I subtract again, I'm going to get 8x squared from there, and from here I'm going to get minus 16x. And let's bring this down here. Okay, remember that's like my remainder, which I'll hook onto the 24, or minus 24. Okay, how many x squareds are there in 8x squared? That's going to be 8. Okay, then multiply 8 by all of this. So you've got 8x squared, take away 16x, take away 24, and the remainder then is 0. So what that means is this original quartic divided by x squared minus 2x minus 3 equals x squared plus 6x plus 8. So what does that mean? It means that if this here was f of x, so if this quartic here was f of x, I can write f of x as x squared minus 2x minus 3, so that's one of the factors. We can see it's a factor because there's no remainder, multiplied by x squared plus 6x plus 8. Okay, and I can actually factorize these out. So let's just factorize the first quadratic. So I've got x and x. I need a 3 and a 1, and it's got to be a minus 3 and a plus 1. And the other quadratic would be it's going to be 4 and 2. It's going to be plus and plus. So if I wanted to solve f of x equals 0, the answer would be x equals minus 1, x equals 3, x equals minus 2, and x equals minus 4. Okay, so hopefully that's shown you how to use polynomial division to work out the factors of a polynomial. Now this is only when the factor theorem applies. There is something else called the remainder theorem when you can't factorize something fully, and I'll do that in a separate video. But this is how you can factorize a any polynomial by using the factor theorem. Now, before I finish, there is one last thing I need to warn you about, and that is when you have a polynomial that hasn't got all the terms in it. So, for example, if I had a cubic like 2x cubed plus 4x minus 5, and imagine I was dividing it by x minus 2. Now, I've just made this up. X minus 2 might not even be a factor of this. Okay, when you're setting it up, you need to make sure you set it up as 2x cubed plus 0x squared plus 4x minus 5. So when you're setting it up, this bit here needs to contain all the components of the quadratic. Okay, whether the coefficient is 0 or not doesn't matter. Okay, it has to be there. And it's a little bit like when you're writing a number. Just because, for example, if I write 2005 like that, just because I've got no hundreds and no tens doesn't mean I'd write it like this. Okay, so with a number, when you've got no hundreds and no tens, you still have to write the fact that it's got no hundreds and no tens. And the same goes with these polynomials. Just because I've got no x squared term doesn't mean I don't include it when I'm actually dividing. Okay, when you're writing it like this, no, we don't need to include it. Okay, but when we're dividing, we do need to include it because it's written as though you're writing a number. Okay, so make sure all the different components of your cubic or quartic or whatever it is are included. Right, so that's it for this video. I hope that's helped. If you need to watch it again at your own pace, please do so. And I think this will be very useful for when you're solving any kind of polynomial equation where f of x equals 0. And if you're doing the further maths course, it's going to be useful for when you're using complex numbers and trying to work out complex roots. So, for a cubic, for example, you might have one real root and two complex roots. And you need to be able to work out where those complex roots come from, in which case you need the quadratic from which you'll work out those other complex roots. Anyway, that's it for now. I hope that's helped, and I'll see you next time. Goodbye.